Broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to the A3 webinar series. Thank you for joining us for today's webinar, Robotic Surfacing, a Transition to Automation. My name is Jackie Rose and I'm the Marketing Communications Manager for the Association for Advancing Automation. I'll be serving as your moderator today. Attendees viewing this webinar are in listen-only mode. It means you are muted. If you have questions during the webinar, you can submit them in the question panel to the right of your screen. We'll try to address as many questions as we can at the end of the program. If your question is not answered during this webinar, we will respond via email. The webinar is being recorded and a link will be sent to you within the next 24 hours. This webinar is brought to you by the Association for Advancing Automation. We're also known as A3. A3 is the leading automation trade association in the world for robotics, vision and imaging, motion control and motors, and the industrial artificial intelligence technologies. We are your hub for all automation resources, products, partners, new applications, trainings, and information on the latest technologies and innovations. Visit automate.org to learn more. If you're attending today's webinar and are interested in robotics and automation, robot safety goes hand in hand. We encourage you to register for our International Robot Safety Conference taking place in Columbus, Ohio, September 27th through the 29th. This conference examines key issues in robot safety and provides an in-depth overview of our current industry standards. I'll make sure I post the link to learn more in the chat in just a little while. And backed by popular demand, our Autonomous Mobile Robot and Logistics Week will take place in Boston, Massachusetts, October 10th through 13th. This conference covers automation technologies in the distribution, material handling, and e-commerce spaces. During the same week and same location, the Vision Show will take place, covering machine vision and imaging technologies. I will also post the link to that registration in the chat. And I'd like to thank our exclusive sponsor for today's webinar, Robot Master. A Hypertherm brand is an offline programming software for robots that helps manufacturers maximize productivity on production runs of all sizes. Robot Master makes programming parts of any complexity quick and easy as a result of its integrated CAD/CAM functionality. This intuitive and powerful solution is designed with process experts in mind, reducing the need for programmers and robotic expertise. And it's now my pleasure to introduce our panelists for today's webinar. Corey John is a software sales manager at Hypertherm, and Nathan Herbst is a robotics application engineering specialist in 3M's Abrasive Systems division. Thank you both for being with us today, and I will now hand this webinar over to you.
Thank you, Jackie. As Jackie said, my name is Corey John. I'm one of the software sales managers here with Hypertherm and the Robot Master product line. As we jump into the presentation, I believe most people are aware that many of the manufacturing applications you see today on the shop floor can be automated. One of the big pushes we see in the marketplace today is around the material removal applications. This can be anywhere from plasma cutting, water jet cutting, milling, trimming, and even surface applications. Today we'll be focusing on the surface applications, which can include things like deburring, grinding, sanding, and polishing. To help deliver a wider breadth of expertise in this field, we invited one of our partners, 3M, to join us on this webinar. They will talk about handheld abrasive operations versus robotic abrasive applications. I will then discuss the different methods that can be used to program an industrial robot for these applications and go over some of the considerations you should make before selecting a method. We will then discuss the specific customer situations, the challenges they were facing, and how the solution helped them overcome the challenges. With that said, let me pass it over to Nathan from 3M for this next part.
Thanks, Corey. Yeah, my name is Nathan Herbst. I'm an application engineer with 3M's Abrasive Systems division, focused on robotics, particularly in the sanding part of the world, heavily focused on automotive at the moment, but I spent a lot of time as well with Scotch-Brite and random orbital sanding. There you go. So here's a list of a variety of different terms that are commonly used for abrasive applications. As you can see, there are quite a few that can lead to some ambiguity. Terms such as blending, radiusing, finishing, sanding, and surface preparation can have different meanings to different people. We've tried to make this a little more clear by defining our 7 primary abrasive applications. These range from very aggressive material removal processes such as cutting, where you're actually taking a larger piece of material, cutting it down into smaller pieces, grinding, kind of like weld, say I've got wire feed welds, MIG welds, TIG welds, sub-arcs, removing material, rolling through the more medium duty applications of deburring, cleaning, satin finishing, and then on the finer end, the orbital sanding and polishing. So what is orbital, or in this case, random orbital sanding? The primary goal of any sanding operation is to generate a matte or nonlinear surface finish. Usually used to make a dull finish free from visible linear or rotary scratches. Often the type of surface left from orbital sanding is really ideal for applying coatings such as paint or lacquer. Consider like a aerospace fuselage or wing, wind turbine blades, things like that, where they're going to get the composite material scuffed prior to coating, painting, a variety of different coatings that can ultimately end up on it. Other applications like are shown in the images here, say a guitar body where we're refining polyurethane. So the polyurethane is applied, it comes on with orange peel, we need to knock that down and then bring it up to a high luster finish with a polishing process. Most common abrasives used for orbital sanding tend to be coated abrasive discs or sheets. These are conventional abrasives applied over a paper, cloth, foam, film backings. The most common grades think of in that 80 to 240 grit range. These are commonly used in wood and composite finishing and sanding. For finish consistency and long life, we also offer micro-replicated abrasives and non-woven products. These can be used for solid surface finishing, particularly on the micro-replicated materials for consistency over time. Similar technology is also used on clear coat finishing and refining, denibbing. Non-wovens are often used to leave a matte or final finish on stainless steel, also in that composite scuffing space. A lot of these tend to be attached with PSA or hook and loop, and usually there is some sort of built-in compliance, either in the holder or backup pad, or the abrasive itself, like in the case of Scotch-Brite or the foam Trizac discs. Now, that flexibility allows the abrasive to conform and follow part contours if necessary. Sorry. When designing an orbital sanding process, you can see some of the key factors here, but 2 of the very important considerations are the finish requirements and part geometry. It's common to sequence abrasives using progressively finer solutions. Think of finishing a door or a table. You start with 60 or 80 grit to remove surface imperfections or maybe existing materials. Work your way up into 240, 320 grit to apply stain and then new polyurethane. It's common to sequence all of them, depending on which ones you're working with, but multiple steps until that final surface finish is achieved. And that's really what is important to understand, is where do you need to get, and also where are you starting. That can really determine the number of steps that are needed. Orbital sanding tools can come in a range of orbits. So larger orbits provide more aggressive cutting action, while smaller orbits tend to generate a finer, duller finish. As I mentioned before, the contours of a part are critical to orbital sanding, so taking the complexity of the part into account, particularly any sort of curved surfaces, can dictate the tooling necessary. That could be interface pads, backup pads, if you need a flexible material, things along that nature. Orbital sanding is one of the most common robotic abrasive processes, particularly because it tends to be one of the easier ones to implement. Not to say any of this is really easy, but there are still a range of important considerations for successful deployment. Once again, we note that force control is important, with some of that coming from the built-in compliance we mentioned earlier in the foam and non-woven products. However, as you work on more complex geometries where parts or tool orientation will vary significantly, that may be required to have active force control. That being, it accounts for tool orientation relative to gravity. So as you go around a part, you know you're maintaining a consistent force. Similar to like a cleaning operation, it's common with orbital sanding to generate a fine dust. So addressing the capture of that dust is important, not only for maintaining cell cleanliness, but also to evacuate dust from the abrasive and part interface, which is where the disc is actually doing its work. If dust builds up there, you can cause loading and lack of cutting or disc life. The abrasives typically used for orbital sanding need a relatively frequent changing. So also it's important to consider automated media changing solutions with the robot cell design for successful deployment. Once you've selected your system, now it's time to consider all the factors that you have available. Robot feed rate, how fast you can go, will really be dictated by the cycle time constraints that you have. How many parts are needed produced per hour? It gives you an idea of how fast the robot has to move to get that done. How much force should be applied? So this can be variable depending on where the disc is throughout its life or where on the part you are. Say if you're on a large flat area, you can push harder. You may want to dial that back as you're going across curved or sharp edges. Spindle speed, how fast should the abrasive be spinning? Higher RPM, higher cut rates, lower RPM, lower cut rates, although coarser surface finish. What orbit should be chosen? Is it a more aggressive blending or removal step, or is it more of a final finishing process? Now that can affect from, say, a 1/2-inch orbit all the way down to maybe a 3 millimeter orbit. Sorry to mix up systems on you there, but think of a large orbit like a buffer or polishing type of tool compared to a very fine orbit like a jitterbug. Finally, are multiple passes needed to help normalize the cut rate, say knowing that a new disc cuts faster than an old disc. So if you're running something where the disc needs to be changed throughout the part life, or throughout the part processing rather, you'll want to make sure you start from the point that the last disc ended and work your way backwards. That allows you to normalize out that cut rate over time. Orbital sanding on very large surfaces, such as an aircraft fuselage or wind turbine, is pretty common. So it's typical to see operators really trying to climb all over these parts, sanding with a 5-inch orbital sanding tool. With robotics, they're ideal. They can reach farther than people can. They have longer arms, so they can cover a much larger area with tooling that may be much heavier than a human operator can handle. So maybe you could have multiple heads mounted on a gimbal to follow different contours. Also, orbital sanders are difficult for operators to run in a straight line if necessary. Say we're not great at following perfectly straight lines, although robots can do this without a problem. One challenge that can cause is striping. So in finishing, it's important to monitor or manage your stepovers to make sure that you're not leaving lines or indications on your surface that you've all your path has been erased.
All right.
Did that execute?
There we go. So
Thank you.
Thank you very much, Nathan. So one of the things that you need to decide once you've decided to automate your processes, how are you going to program the robot? There are a lot of things to consider, but really we've narrowed it down to just 4. The first thing, and probably one of the most, the biggest ones for customer is the learning curve, as downtime costs money. You want a solution that is quick to learn and leans on the person's process expertise to use the robot as just another tool in their toolbox. The second is the production style. You'll need to look at if you're going to be running parts like a job shop or a prototype lab where you could be processing runs of maybe 1, 10, 100, or even 1,000 with a high mix, low volume model. Or will you be doing runs of 100,000 plus in a production run or an assembly line? The next thing is complex shapes. The company will need to review the types of parts that they are working on to see if the programmer can have the confidence to be able to reproduce the results consistently. And finally, the finish and repeatability. Being able to meet the customer's expectation with stringent requirements, such as in the aerospace industry, can be a big deciding factor when selecting a programming method. So when you're looking at programming a robot, really there's 2 main programming methods. The first one, and the one that you see out there quite a bit, is the teach-pendant programming method. This method involves using a controller at the robot and has the end user match up locations with the robot tool to the part by visually moving the robot to a precise location and recording a point. This method can be time consuming and is only as good as the programmer's eye. Once the project has been taught with the controller, the output is a program that is specific to that brand of robot and that specific robot arm and cell. The second one is an OLP software or an offline programming software. Similar to using a CAM software to program CNC machines, an OLP software is a popular programming method in the industrial robot space. Offline programming software enables the user to program the robot on a computer. Since this action is independent of the hardware, you don't need to take the robot out of production to program. By importing the CAD model of the part, the software can automatically generate the path trajectories and create the programming in a matter of minutes. The OLP software also provides programming optimization and validation through the virtual simulation environment that matches the real-world robotic cell to ensure the generated program is error-free and collision-free. So let's look at the teach-pendant programming against the 4 considerations that we discussed earlier. The first one is what it comes to is the learning curve. First, it requires somebody with robotics expertise and coding expertise. So not only are you jogging the robot around to find the specific location, the correct tool vector, and staying normal to the surface, but once you've created all the points, you have to understand the syntax, maybe entering some logic or some macros to be able to get the program to run correctly on your robot. It's also a trial and error process to achieve desired results, even with the most experienced user. And teach-pendant programming is very language orientated for each robotic brand. When working with complex shape, it can also create issues with hard to reach areas and can be very problematic and time consuming when programmed via teach-pendant. You also increase your risk of collisions between the tool and the robot and the part. Production style is a big one, as in low mix, high volume application, this method offers an excellent ROI. A single programming job can sustain productions for a long time. And finally is the repeatability, as it allows for on-the-fly adjustments for a variety of parts or desired finishes, and is subject to human error, even nearly impossible to achieve the same results every time. Now let's compare this programming to an offline programming software and the 4 variables. First one is the learning curve. Most offline programming softwares are easy to use and easy to learn and have a workflow for users with little to no experience in programming robots in the past. Really what it requires is somebody to be comfortable with using a computer. You really don't need to be a robotic expert to program. Includes easy-to-use optimization and error-free correction tools. Uses the same programming interface for all robots, eliminating the need to be familiar with multiple different systems. When it comes to complex shapes, offline programming software is generally built with powerful tools that make programming complex parts very easily. RobotMaster, as an example, includes tools to automatically optimize the path to avoid collisions, robot errors, and reduce cycle times. This solves a lot of issues when programming complex part profiles, making it easy to program the hard-to-reach areas. And the production style. In a high-mix, low-volume applications, programming time is extremely impactful to margins. The ability to quickly and flexibly program more jobs also greatly improves productivity. Finish and accuracy and repeatability. An OLP software takes the CAD to path approach. The program can be created based off a feature off the CAD model. And some OLPs like RobotMaster give the users the ability to save the strategies, or what we call them recipes, used in a programming library that can be later called upon and distributed across many facilities. So once again, how does an offline programming software work? The first thing that you do is you bring in your CAD model, right? So you have a CAD model of your part. From there, you use all the information that's built into that CAD model, all the different surfaces in there, and able to use that information to drive the trajectories or the tool vectors to make sure that you're normal to the surface. So very easily being able to create complex paths on there. From there, once you have the paths that you're happy with, you can bring it into the simulation environment to take a look at, am I going to have any robotic issues? And if you do, have the tools to help automatically fix those. And once you have a program that you're happy with and it's error-free, have the ability to output the code for whatever robot brand that you're looking to use. Another key benefit, especially in the service finishing, is the ability to take a root path or a straight path and add in different kinds of strategies there. So where trying to program a figure eight or a triangular path with a teach pen, it would be virtually impossible. For us, it's just a one-click method. So adding in from those straight lines, the ability to add in the figure eights, the triangular or tricoidal is very easy to do. Another key benefit of the OLP software is really it drastically reduces programming time and effort when it comes to the high mix, low volume production runs. Optimization of the path also avoids errors and collisions, maximizing profitability and increases the robot return on investment. So let's talk about one of my customer journey when it comes to automating in a surfacing application. So McStarlite, the world's leading producer of aircraft engine lip skins since 1973, based out of California, produces some of the largest and most complex sheet metal components for the aerospace industries. McStarlite was looking for a way to improve their polishing application, as it has been done by hand, which takes a physical toll on workers and is very time consuming. Another downside to hand polishing in the part is inconsistencies. As a surface finish is only as good as the skill of the individual labor, and components have to be reworked to meet the stringent requirements within the aerospace industry. This additional rework and cycle time cuts into the profitability of this operation. In 2020, McStarlite invested in automation by integrating a KUKA robot cell coupled with RobotMaster to perform the lip skip polishing application. For those who are not aviation experts, the lip skin is the aerodynamic structure that makes up the leading edge of the airplane's engine. With automation, they are now able to deliver consistent and accurate parts at a fraction of the time, ultimately allowing them to meet the demand and the stringent requirements from the aerospace industry. RobotMaster's ease of use and flexibility enabled the McStarlite team to manipulate process-specific parameters and achieve the optimal feed rates, RPM, forces for each one of their passes. Alongside their improvement in their production, enhancing working conditions for the laborers and operators was a priority for them in looking in their next investment for their organization. The type of manual labor being performed prior to automation was very hard on the laborer's back, legs, and even arms. It was a priority for McStarlite to provide a better working environment to its people, which is why a user-friendly tool like RobotMaster was the ideal choice. Working with the vice president at McStarlite, he had said that we are very proud to keep the same people that were doing a manual labor and train them to be operators. RobotMaster's simplicity of use enabled the repurpose of people that were doing a manual labor now to use the robot. The opportunity to reduce cycle times and increase production is a key feature in OLP software. The unique value that RobotMaster delivers for McStarlite is not just the simple-to-use interface that allows the operator with no previous experience programming robots to be able to do so, but the path optimization and capabilities to change the game for them. RobotMaster provides instant feedback of issues and opportunities to quickly obtain optimal robot programming. Instead of the frustrating hit-and-miss approach, operators can quickly and easily ensure their programs are error-free, and high mix, low volume production facilities especially benefit from this technology as it greatly improves their cost efficiency. Saravana and Quality had said that automation is something that they had wanting to do for over decades. It's a lot of planning and CapEx. However, the automation allowed them to standardize the finish and the consistency improve their cycle times. By taking a leap into automation, McStarlite can deliver consistent high-quality parts to Airbus, reducing cycle times and meet the demand for the polished lip skin. Now being able to maximize profits and quote lower prices on future programs, McStarlite can be much more competitive and take on new opportunities and projects. They have plans to add additional robot cell components such as a rotary table to ensure them to polish larger products such as full engine cowlings. We look forward to being a part of their journey as they continue to expand their capabilities. Service technologies for robots material removal are enabling manufacturers to increase productivity and profitability and achieving higher quality finishes. Customers like McStarlite are seeing huge benefits, and we'd be happy to assist you as well in your transitions to automation. Are there any closing thoughts from you, Nathan, before we roll into Q&A?
Not at the moment. I'm ready for any questions.
All right.
So thank you both so much. We do have some questions coming in. This first one looks like it's for you, Nathan. How applicable are collaborative robots for orbital sanding, and what should somebody consider when selecting that robot?
The big things to consider in any abrasive process when it comes to collaboration are running a safety analysis on the application. It's, putting people next to a robot that's going to be running a tool with an abrasive disc that's spinning still has to be analyzed from a safety standpoint. The robot may stop when it makes contact, but that disc can still cut and hurt somebody. So it's really important to make sure that you're managing the safety of those employees that are going to be working near a collaborative robot. When it comes to payload, that's one beauty about collaborative robots is the random orbital process is fairly light duty compared to maybe some grinding or cutting applications. So there's certainly some opportunities for collaboratives in the random orbital space, but the environment still needs to be analyzed from a safety standpoint.
Great, thank you. This next question, Corey, is for you. What kind of ROI can we expect from switching from teach pendant to software-based programming?
Yeah, absolutely. That's probably the biggest question when it comes to looking at a software is what is it going to take to repay this purchase? A lot of times when you're looking at adding a software solution to a company, they're looking for roughly around a 6 to 8 month return on investment. With RobotMaster, I've seen this be cut down into 1 or maybe 2 program parts. What used to take 40 hours to program previously can be now done in 15, 20, or 30 minutes. We've even seen programming times that was taking 30 plus days to program by hand, a very large polishing application, be cut down to less than an 8-hour workday. So the ROI can actually come very, very quick.
Absolutely. And this next question is also for you, Corey. How does the software handle unexpected situations? For example, a lip skin blank is not exactly matching the normal CAD. How much variation can be managed?
Yeah, a lot of this can come down to when the integration of the robot. As Nathan had said, there's several different tools that you can use to try to match the nominal world to the real world, right? So, the force compliance in there can help keep the robot in a constant contact point. Some software, some applications with OLP will be used some vision systems or some laser guiding. So There's a lot of different tools that can be set up in the integration side of it, connected to the controller to take that nominal path to match the actual real world.
And Nathan, what industry do you feel has the most application for robotic deburring?
Deburring, I mean, to me, it's the machining industry. There are many CNC machines out there. A common application is to use a robot to tend that machine, to take a finished part out, install a new piece of raw material, and set the machine running on the next part. So as a deburring step, many of these parts coming out of CNC machines get either deburred or maybe a small edge radius applied, and that would be an opportunity for the machine tending robot to also do that small amount of work. So I think in the casting, forging, machining space is really where a lot of that opportunity is.
Yeah, absolutely. And could you also comment on end-of-arm sanding using pneumatic tools versus electric or servo-driven tools, the benefits or disadvantages of each?
Sure. So the primary benefit of using a pneumatic tool at the end of a robot, say the example of the collaborative, they're not very heavy. So they're fairly lightweight for the power they generate. The primary drawback or advantage of the electrical and servo devices is speed control and consistency over time. So a servo motor or electric tool will run its variable RPM, so you can tell it how fast you want it to go. You can vary that and fine tune it for your process. But also, it won't change over time. You're going to get what you are commanding from it. Air tools have to be oiled periodically. That can be potentially negative or not allowed in certain applications as far as the use of oils. To maintain consistency, they also have to get rebuilt more frequently. So it's the main benefit of servos is over time, consistency and variability or control of it. Also, when it comes to disc changing, servos can help because a random orbital tool, it doesn't always end up in the same place. Particularly an air tool, you turn it off, it's going to end up wherever in its orbit it is. Where the servo motor, you can drive it to a known position, which then allows you to maybe do disc changes more easily.
Great, thank you. Corey,
Absolutely.
back to you. When working with these systems, do you recommend working with an integrator?
Yeah, I think, anytime that you're trying to match up a software program to the robot, a key partnership is your integrator, right? So the ability to, like I said, trying to match that real world to the nominal world, the ability to, help set up any callouts or macros that need to be done. And really, it's a partnership between the end user, the integrator, and the software provider is what's going to make you successful in programming.
Absolutely. Corey, also for you, somebody was asking for marine applications. Our boats have a lot of fiberglass parts, but these parts are made per boat. Would one robot be able to polish 15 unique parts, or would that not make sense?
I mean, if the robot, can reach and be able to, get those paths on there as inside their wheelhouse, then I don't see why it would be an issue by having more than one robot. So as long as you're able to present the part in front of the robot in a manner that it can reach, run through the paths and go, I don't see it being an issue. But it's something that, I can reach out to you directly to be able to see if it's a good fit for you.
Great. We'll be sure to pass along all of these questions and the contact information as well.
Absolutely.
So you can contact them that way. Perfect. Nathan, how do you determine when to change an abrasive disc to a new one?
A lot of that is done currently based on empirical data. So running the disc, and that's through what a lot of the proof of concept and early support can do is on example parts, determining how long discs last. A common application or a common use for manual sanding is estimated about half the cut rate. That's when the disc will get changed out. People feel that they're pushing too hard or it's not working fast enough. With robotics, it gives you an opportunity to kind of modify that. So you can start, say if you're getting the cut rate you need at 5 pounds of force. As that disc starts to wear and the cut rate drops, you can start increasing the force if the part is able to handle it. So you can maybe bump that up to 7, 8, 10, 12 pounds to continue to get the disc to work. But it's really through a lot of process development and optimization that you'll get there to fine tune how long that disc lasts.
Yes. Corey, could you talk to the training process for Robot Master, how long it might take and what that process looks like?
Yeah, absolutely. The training is actually quite easy. Even if you're taking somebody who has never touched a robot before, but has, some process knowledge, right? So what is it that you're trying to do to the part? Really, it's probably 2 to 3 days of training. I know myself, when I was getting into robots and the RoboMaster product, as a sales guy, I was even able to pick up the software and start programming customer parts in less than 2 days. So the software is pretty intuitive. It's very easy to use, clean user interface. So being able to program complex parts can, like I said, be a matter of minutes instead of hours that we've seen in the field.
Always so cool for me to hear. Also, as somebody who's not a robotic expert, that's great. Nathan, for dust extraction in a robotic cell, could you talk on using a central vacuum system versus a local extraction unit near the cell?
Sure. So there's different options available. The central vac system is more ideal in the case that it allows a higher level of collection without having to change out, say change out a bag more frequently. If the application is such that you can't have hoses running down the arm of the robot, there are local collection options like self-generated vacuum with some air tools that can be used, but for an automated application where you want to set the robot and let it continue to run, anytime you have to go into that cell and change out a bag or a consumable is going to be downtime. So ideally, a central vac is probably the better option if the system allows for it.
Perfect, thank you. Corey, does Robot Master help identify robotic reach limitations, and how does it accomplish this?
Yes, absolutely. Obviously, as we talked about the boat standing previously, RoboMaster has the ability to create what we call the workspace analysis. So what it does, it actually creates a real-time rendering around the robot that'll show you the reach that's capable. So it looks at the size of the robot, the joint limits, how you have it configured. Is it hanging from a ceiling or on a wall? Are you in elbow up or elbow down position? So it actually takes a look at all these different scenarios and says, where can the robot reach? And then if the path is outside of the reach of that, it actually goes from, it actually traces it all out, goes from a green to a red. So you can actually see where your problem areas are. So either you can look at rotating maybe around the Z of the TCP to be able to get a better reach of it, or look at maybe just sliding the part in until that path gets inside and turns green. So like I said, very easy to be able to take a look at what the reach of the robot is and where specifically you should probably put your parts to get the best programming options.
Thanks. And also, Corey, a question for you again. Is there any delay when generating the G code?
No. So once you have a that you've created, it's in the software, simulation is good, exactly how you want it. Really, it's a one button click. Once you click it, it creates the points. Can be anywhere from 100 points to 600,000 points, and it can be just a matter of maybe a minute to be able to create that. So once you have that program, you put it on a thumb drive or on the shared FTP site, and actually bring it out to the robot directly to be able to run it.
And Nathan, this question back to you. My operators prefer to use a highly compliant interface pad between the abrasive and the holder on the tool. How common is it to use an interface pad when performing this process robotically?
It's not uncommon, particularly to account for minor angular offsets when it comes to presenting the tool to the robot. It makes disk changing more difficult because interface pads are tough to remove just the disk and not pull the interface pad off. But that being said, there is the benefit of them when it comes to making up for minor angle offsets. So they're used fairly often.
Okay, good to know. And Corey, do you offer any trials with the software?
Yes, actually, if you go onto our website and request more information, we can take a look at setting up a trial.
And what is the website? Somebody was asking how they
yeah.
might get started.
www.robotmaster.com.
Perfect, easy enough. Thank you. I'm just doing a scroll here. Yep, we got some more coming in. Corey, when the work piece is bigger than a single robot reach, how does the programming work?
Well, there's a couple different ways that you can do it. One is obviously you can fixture it, right? So you can have the one location, work it till completion, and you can refixture it. If you have the ability to have a robot on a track, obviously helps out with the reach along a linear rail. You could use a rotary table, so if you need to be able to get to the other side of it, the part can actually spin. All this stuff can be programmed inside of RobotMaster. So the ability to, work with inside the limits of your robot is pretty easy.
Perfect, thank you. All right, folks, it looks like that is all of the questions that we have today. If your question was not answered, as a reminder, I will send these on to the team here, and they will be answered via email. So with that, I would just really like to thank you both, Corey and Nathan, for your time and your expertise. And I'm going to come back on and I will close us out.
Thank you.
Perfect. So I will invite everybody on the call here to join us next Thursday for our next webinar. And that is hosted same time, same place, 2 p.m. I saw the 2 and thought it was 12. We would invite you to learn more and register for free at automate.org/webinars. We hope you found this webinar to be interesting and informative. If you have any questions about the Association for Advancing Automation or today's webinar, please reach out to RobotMaster or myself via the contact information you see on the screen. As a reminder, this webinar has been recorded, and an email with a link to the recording will be sent to you in the next 24 hours. Thank you again to Corey and Nathan for a great presentation, and thank you to RobotMaster for your sponsorship, and to all of our listeners today for your support. We invite you all to stay safe and healthy, and we hope you have a wonderful rest of your day.